All right, let's take a look at question number 4. We are to find the derivative of y equals sine e to the 3x plus 2 raised to the 4 tan x. All right, so whenever you see a situation like this where you have y equals a function raised to another function, the best method to use is logarithmic differentiation. Okay, so we're going to be using logarithmic differentiation so we can gain easy access to this exponential function right here. All right, but if you have y equals a number raised to a function, you can use the rules of differentiation, namely the exponential rule for differentiation, to differentiate this situation. Okay. All right, so let's go ahead and set this problem up. So we have y equals sine e to the 3x plus 2 raised to the 4 tan x. All right, so we're going to take actually 4 to the tan x. We're going to take the logarithm, the natural logarithm of both sides of our equation. Okay, if we do that, we're going to have the natural logarithm of y equals the natural logarithm of this entire right side, which is sine e to the 3x plus 2 raised to the 4 to the 10x. All right, so using the properties of logarithm, we can power down this function right here that is a power. We can just power this down right there. Okay, it becomes a coefficient of this logarithmic expression. So we have the natural logarithm of y equals 4 to the tan x times the natural logarithm of sine e to the 3x plus 2. Okay? Now we are going to differentiate implicitly. Okay? Remember, you use implicit differentiation to find the derivative of equations that are not explicitly solved for y, as we have in this case. All right, so if we differentiate the left side, we're going to have 1 over y, because the derivative of ln y is 1 over y, using the implicit differentiation times y prime, which is the same thing as dy dx. And if you take a look at this side right here, we're going to have to use the product rule. We have the product of two functions, all right? The first function, 4 to the tan x, we can call that u. And then the second function, we can call that v, all right? So to find the derivative, we're going to use the product rule. So we know what the product rule is. U v prime is equal to v u prime plus u v prime. All right, so there goes your product rule. Okay, so let's go ahead and do this. So what we're going to do, we're going to have the natural logarithm of sine of e to the 3x plus 2 times the derivative 4 to the tan x prime plus u, which is 4 to the tan x, times the derivative of this other function, the natural logarithm of sine of e to the 3x plus 2. Okay, so that's prime. Now, I have a lot of tutorials that I've gone over where I go into detail as to how to apply the chain rule. I'm not going to do that here. We're going to cut corners a little bit. So I'm going to finish this problem, assuming that you have a solid grasp on how to carry out the chain rule on multiple, on functions that are made up of a composition of more than two functions, okay? Multiple compositions. All right, so let's go ahead and finish this off. I can multiply both sides of my equation by y. Remember, the problem asked us to find y prime. So we can multiply both sides of the equation by y, and then multiply this entire equation by y. All right? Okay, so I'm going to leave that out for a second. Let's go ahead and differentiate this piece right here. So we have y prime equals y multiplied by, now we are going to have just this piece, the natural logarithm of sine e to the 3x plus 2. Remember, for this problem, you do not have to simplify, okay? So just keep that in mind. All right, so differentiate this. We're going to use the derivative of exponential functions. So we know a to the x prime is equal to 1 over a times the natural logarithm 1 over a to the, is this a to the x times the natural logarithm of a. Okay, let me correct that real quick. So it's a to the x times the natural logarithm of a. And also we're going to be finding the derivative of tan x, which is a composite function. We know that the derivative of tan x prime, is secant square x. Okay? All right, so we're going to apply that in the differentiation of this function right here, 4 to the tan x. So the derivative of the alpha function is a to the x ln a. So we're going to have 4 to the tan x times the natural logarithm of the base, which is 4. So that's the derivative of the outer function, times the derivative of tan, which is secant square x. Okay? Now, we're going to differentiate this part. We're going to do uv prime. So u is simply 4 to the tan x. Now let's differentiate this. To differentiate the natural logarithm, let's go ahead and go over the rules over here. Ln of x prime, we know what that derivative is. It's 1 over x. And then we know what the derivative of e to the x is, right? The derivative of e to the x is e to the x. And then if we're differentiating a power, the derivative of a power is n x to the n minus 1, which is what we'll use to differentiate 3x. Okay? Now, let's go ahead and do it. If we differentiate the natural logarithm function, the outermost function, we're going to have the reciprocal of the logarithmic argument. So we can basically send that downstairs to conserve space. We're going to have sine of e to the 3x plus 2. So we've differentiated the logarithmic function. Now we're going to go in, differentiate the sine, derivative of sine. Oh, I skipped that. We know what the derivative of sine is, right? Let's put that there. The derivative of sine prime, sine of x prime is cosine x. Okay? So if I differentiate sine, which is the next function, we have 4 functions here. When I differentiate sine, I'll have times cosine of e to the 3x plus 2. That's the derivative of the sine. Now I'm going to go in and differentiate e to the 3x plus 2, term by term differentiation. If I differentiate e to the 3x, I'll have e to the 3x. If I differentiate 2 plus 0, I don't need to add that there. Okay? So plus 0. And then we're going to differentiate the innermost function, which is 3 to the x. The derivative of 3 to the x is 3. Okay? So there goes your, that's uv prime. All right, so for the test, if you go this far, that's you get full credit. What I'm going to do now is I'm going to make it look pretty. Okay, just dress this up a little bit so we have a nicer looking at result. What can we do here? Now, if you inspect this equation, what you notice is that you have 4 to the tan x as a common factor in both terms on the right. Okay, so how about we go ahead and factor that out? So we have y prime, the derivative, what we're looking for, equals 4 to the tan x All right, and then y is the original function, which is sine e to the 3x plus 2 raised to the 4 to the tan x. So let's go ahead and put that here. So it's sine e to the 3x plus 2 raised to the 4 to the tan x. Okay, now in here, since 4 to the tan x has already been factored out, we're going to have ln 4, the natural logarithm of 4, times secant square x times the natural logarithm of sine of e to the 3x plus 2. Okay? And then on the right side of the plus, if you notice, the argument of our sine and cosine functions are identical. So we can use a trig identity, namely the quotient identity, to write this as cotangent e to the 3x plus 2. Okay, so we can write this as cotangent of e to the 3x plus 2 times 3e to the 3x. All right, so there goes your final result. Go ahead and box it.